Bismillah wa salatu wassalamu ala rasulillah. Welcome to General Chemistry with Dr. Zainab. Today we are going to solve recitation problem for chapter 3, which is about stoichiometry, ratios of combination. Please make sure that you have your periodic table available with you with the molar mass of the elements. Let's start with problem number 1. Complete the following table. We have the mass of the sample, the mole of the sample, the molecules in the sample, and the total atoms in the sample. For the first question, we have 4.24 gram of C6H6, which is benzene. Okay, and they're asking us to calculate here the number of mole and the number of molecule, and finally the total atoms in the sample. So let's remind the relationship between the number of mole and if we have the mass of the sample, it's going to be M divided by the big M, which is the molar mass. So let's start by calculating the molar mass of benzene. So it's C6H6. So the molar mass will be equal to 6 times the molar mass of carbon plus 6 times the molar mass of hydrogen. And the molar mass of carbon is 12.01 plus the molar mass of hydrogen, which is 1.008. We always get 4 significant figures when it's come to the molar mass. And here, if you calculate it, it's going to be 68.11, and the unit is gram per mole. Now that we have the molar mass of benzene M, we can calculate the corresponding number of mole. So it's going to be 4.24 divided by 78.11. And here we have 3 significant figures, 4 significant figures. It's a division, so the result should have 3 significant figures. And if you calculate, it's going to be 5.43 10 to the power minus 2 mole. So we have 3 significant figures for the result. So this is the number of mole corresponding to the mass of 4.24 gram of benzene. Now that we have the number of mole, so here we can write it, 5.43 10 to the power minus 2 mole. What will be the number of molecules? What is the relationship between the number of molecule and the number of mole, or how to get from one to the other? What we know is 1 mole of anything, that's here benzene, correspond to 6.022 10 to the power 23 C6H6. Here molecules. And here molecules. So for 1 mole of C6H6, we have 6.022 10 to the power 23 C6H6. Here the number of mole we have is 5.43 10 to the power minus 2. The result will be 5.43 10 to the power minus 2 multiplied by 6.022 10 to the power 23. And when you divide it by 1 mole, so there is no more units, it's going to be C6H6. So here is in mole. Okay. And if you calculate it, it's going to be equal to 3.27 10 to the power 22 C6H6 molecules. Okay. And still the significant figures, we have 3, because at the beginning we have a number with 3 significant figure, and here we have 4. So the result should have the smaller number of significant figure, which means 3. Okay, so we have 3.27 10 to the power 23 benzene molecules. So here we can write it down. Now, what is the number of atom, total atom? In C6H6, we have 6 carbon atom and 6 hydrogen atom. So we have 6 times more this one, 3.27 10 to the power 22 carbon atom, and 6 times 3.27 10 to the power 22 hydrogen atoms. So if you want the total number of atom, for C6H6, it's going to be 12 because I have 6 times plus 6 times, so 12 times 3.27 10 to the power 22. And if you compute it, it's going to be equal to 3.92 10 to the power 23 atoms in total. So it's the number of carbon atoms plus the number of hydrogen atoms. So 12 times 3.27 10 to the power 22. So here to solve it, you need the relationship between the mass and the number of mole to calculate the number of mole. And from the number of mole, the relationship between mole and the Avogadro number, 6.022 10 to the power 23. And then we have the molecular formula of the compound. So we know the number of each atom, how much we have. So we know here we have 6 carbon atom and 6 hydrogen atom. So we know we have 12 atoms in total. So if you multiply this one by 12, we get the total atoms in the sample. So this was for the first question. Okay, we just move on for the second one. In the second one, we don't have the mass, but we have the number of mole. And we know that it's water, H2O. So first, let's write H2O. And we are always going to use the relationship between the mass and the molar mass. So M divided by big M, molar mass, it will give you the number of mole, which is in mole here. So we're going to use this relationship all the time. Okay. Here we have the number of mole. So if you want to get the mass of H2O, we will need the number of mole of H2O multiplied by the molar mass of H2O. So let's first calculate the molar mass. The molar mass of H2O equal to 2 times the molar mass of hydrogen that you can get from your periodic table, plus 1 times the molar mass of oxygen. And it will be 2 times 1.008 plus 16.00. And if you calculate it, it is equal to 18.02 gram per mole with 4 significant figures. So the mass that was initially used for water will be equal to the molar, the number of mole, which is 0.224 times 18.02. Always keep in mind the number of significant figures. We have 3 here, we have 4 here. The result should have 3 significant figures. And if you calculate it, it is equal to 4.04 gram. So the mass here is 4.04 grams of water. Now we have the mass, we have the number of mole. We need to calculate the number of molecules in the sample. So similarly than on the previous exercise, we know that 1 mole of water will give 6.022 10 to the power 23 water molecules. Here we have the number of mole 0.224. So if 1 mole H2O corresponds to 6.022 10 to the power 23 molecules of water. 1 mole, we have 6.022 10 to the power 3 molecules of water. If we have 0.224 mole of H2O, it's going to be corresponding to what? 0.224 times 6.022 10 to the power 23. And if you calculate it, this is equal to 1.35 times 10 to the power 20 H2O molecules. So here we can write the number 1.35. So we have three significant figures, 10 to the power 23. This is the number of water molecules in the sample H2O. And similarly then for the previous question, for H2O, you have 2 atoms of hydrogen and 1 atom of oxygen. So the number total of atom will be 3. So the total number of atom and atom will be equal to 3 times 1.35 10 to the power 23. And if you calculate it, it is equal to 4.05 10 to the power 23 atoms. So both atoms of hydrogen and oxygen, the total number. So let's go to the third question. So here we don't have the mass, we don't have the number of mole, but we have the number of CO2 molecules. Okay, so we know that 1 mole of CO2, now you know this relationship, corresponds to 6.022 10 to the power 23 CO2 molecules. So if I have 2.71 10 to the power 22 CO2 molecules, how many number of mole it will correspond to? 2.71 10 to the power 22, so I do this one, divided by 6.022 10 to the power 23, and this is equal to 0.0450 more. I have 3 significant figures, 4 significant figures. The result should have 3 significant figures. That's why I put 0.0450 more. So the number of mole here is equal to 0.050 mole of CO2. Now that we have the number of mole, so this is N CO2, we know that it's also equal to the mass of CO2 divided by the molar mass of CO2. So let's calculate the molar mass of CO2. MCO2 equal to 1 times the molar mass of carbon plus 2 times the molar mass of oxygen. So it's equal to 12.01 plus 2 times 16.00. And this is equal to 44.01 gram per mole. So we can deduce back here the mass of CO2, which is equal to the molar mass of CO2, 44.01, times the number of mole of CO2, 0.0450. 3 significant figures, 4 significant figures. The result should have 3 significant figures. And if you calculate it, it is 1.98 gram. So at the beginning, we have 1.98 gram of CO2. Now, in CO2, we have 1 carbon atom and 2 oxygen atoms. So the number of total atoms will be equal to 3, 1, and 2 times 2.71 10 to the power 22. And if you calculate it, this is equal to 1.13 10 to the power 22 atoms. Or we can fill it here. 1.13 10 to the power 22 atoms. So let's do the last one. For the last one, we have methanol. So here we have the total number of atoms. So here, if I have methanol, CH3 OH, I have 1 carbon atom, 4 hydrogen atom, and 1 oxygen atom. So in total, I have 5 type of atom. 5 atom in total. 6. Okay. 4 plus 1, 5 plus 1, 6 atoms in total. So if I want to know the number of molecules, I will take the total number of atoms in the sample, 3.35, 10 to the power 22, divided by 6. And if you compute it, you will have 5.58, 10 to the power 21, CH3OH molecules. Methanol molecules. So here we can put 5.58, 10 to the power 21 methanol molecules. Okay, now we have the number of molecules. We can go back to the number of mole. We know that 1 mole of methanol correspond to 6.022 10 to the power 23 methanol molecule. So if I have 5.58 10 to the power 21 CHOH molecule, will correspond to how? The number of mole N of methanol will be equal to 5.58 10 to the power 21 divided by 6.022 10 to the power 23. 3 significant figures, 4 significant figures. The result should have 3 significant figures. And if you calculate it, it is 9.27 10 to the power minus 3 mole. So the number of mole of methanol is 9.27 10 to the power minus 3 mole of methanol. Now we have the number of mole. We can use the relationship between the number of mole, the mass, and the molar mass to get the initial mass. So we know that N methanol equal to M methanol divided by M methanol, which is the molar mass. So let's calculate the molar mass of methanol. M CH3OH. So we have 1 times the molar mass of carbon, 4 times the molar mass of hydrogen, and 1 times the molar mass of oxygen, and this is equal to 32.04 gram per mole. So the mass corresponding to 9.27 10 to the power minus 3 mole of methanol is equal to 9.27 10 to the power minus 3 times 32.04, and this is equal to 0.297 grams. 4 significant figures, 3 significant figures, 3 significant figures for the result. So here we have 0.297 gram of methanol. So that's it for this exercise. You have to know the relationship between 1 mole of any substance and the number of the substance, the number of molecule of that substance, so the Avogadro number, to get from the number of mole to the number of molecule, and to the number of molecule to the number of mole, and also the relationship for any compound between the number of mole, the mass, and the molar mass. And that is enough to solve this problem. So let's continue with exercise number 2. So 752 gram sample of impure iron ore is heated with excess of carbon. So we know that this is in excess, producing 453 gram of pure iron by the following reaction. So we have iron oxide, this is iron trioxide solid that react with carbon solid to give iron solid and carbon monoxide gas. This reaction happened at very high temperature, and actually this carbon monoxide is further oxidized to give CO2. But for this problem, we just stop on the step where we get carbon monoxide. So let's analyze this problem. The question is, what is the mass percent of iron trioxide in the impure iron ore sample, assuming that iron trioxide is the only source of iron and that the iron is 100% efficient. So here, make sure, because here it's like iron 2 times oxide, okay? But in the formula, you have iron 3. The oxidation state is 3+, meaning iron 3+, okay? That's why it's confusing. But here you have 2 times iron, 3 times oxygen, but you have iron 3, okay? The oxidation state. So you have, this is the cation, and the anion is O2 minus the oxide, okay? So be careful. You have 2 times iron, but it is iron 3. Okay, iron trioxide, and since it's an ionic compound, you just need to take the name of the cation, the name of the anion, and you remove ion in between. So that's why it's become iron trioxide, because there is iron 3 and iron 2. Okay, so when I say Fa2O3, I'm not talking about the oxidation number here. I'm talking about the stoichiometry. You have 2 times iron and 3 times oxygen. Okay. So that was the first remark here. Now, what is the mass percent of iron trioxide in the impure iron ore? So we have impure iron ore. So we have iron ore in the sample. In this 752 gram, we have iron 2O3, but we have other impurities. So this is a reaction that we use to purify it and get pure iron. So the stoichiometry of the reaction is telling us that 1 mole of iron oxide equivalent to 2 mole of iron solid. Okay, and we know that all of the iron here that is formed is coming from the iron oxide. So here we get the mass that is produced. We get the 453 gram of pure iron. So M of iron solid that is produced from the reaction is equal to 453 gram. So we can deduce the number of mole. N of iron solid will be equal to mass of iron solid divided by the molar mass of iron solid. Okay, so here we need the molar mass of iron solid and also the molar mass of our oxide. So let's start by that. Molar mass of iron solid, if you look on the periodic table, equal 55.85 gram per mole. And you can deduce the molar mass of iron oxide, which is equal to 2 times 55.85 plus 3 times 16.00, which is the molar mass of oxygen. And if you calculate it, should be equal to 483 gram per mole. Okay, so we have our molar masses and we have our number of mole of iron. So here it will be equal to the mass of iron that is produced, 453, divided by the molar mass, which is 55.85. So we know that 1 mole of iron 2 oxide, iron Fa2O3, okay, give 2 mole of iron solid. So if I have 453 divided by 55.85, 0.85 mole of iron solid, it should give what? Should give 453 times 1 divided by 2 times 55.85. So this is the number of mole of iron oxide. So from the number of mole, I can deduce the mass of iron oxide. So here the formula, the mass of iron oxide initially will be equal to the number of mole times the molar mass. I put everything in one calculation. So we know the number of mole is 153 times 1 divided by 2 times 55.85. And we need to multiply by the molar mass, which is 483. And if you calculate that, this is equal to 648 grams. So from my 752 initially, only 648 grams are actually iron oxide. Okay, so I can calculate the percentage of iron from my initial sample. It should be equal to the mass that we get divided by the initial mass, which is 752 times 100. And it will be equal to 86.2%. So check all of the significant figures. So here you have 3, so it gives 3. Here you have 3, and you have 4, 3. So the result should have 3 significant figures. So this is a simple application where you can use the relationship between the number of mole, the mass, and the molar mass. So let's move to exercise number 3. Terephthalic acid contains only carbon, oxygen, and hydrogen. We have only carbon, oxygen, and hydrogen. The mass compositions were found to be for carbon 57.85, for hydrogen 3.64. So knowing that there is only carbon, oxygen, and hydrogen, we can deduce the percentage of oxygen. If the 0.250 mole of terephthalic acid has a mass of 41.5 grams, determine the molecular formula of terephthalic acid. So we need to determine the molecular formula of terephthalic acid. So from the information that we have, we know that terephthalic acid has only carbon, so CX, oxygen, hydrogen, HY, and oxygen. We know that the percentage of carbon is equal to 57.85. The percentage of hydrogen is equal to 3.64. Knowing that we have only carbon, hydrogen, and oxygen, we can deduce the percentage of oxygen to be equal to 100 minus the percentage of carbon plus the percentage of hydrogen, which is here 3.64. And the percentage of oxygen is therefore equal to 38.51. So we have the percentage of all of our elements. The other information we have is if we have a mass of terephthalic acid that is equal to 4.15 grams, it will give a number of mole N equal to 0.250. So what information can we extract from these two values? Yes, we need to use the relationship between the number of mole, the mass, and the molar mass. So we know the number of mole, we know the mass, we can deduce the molar mass of terephthalic acid, which will be equal to the mass divided by the number of mole, meaning 41.5 divided by 0.250. We have 3 significant figures, 3 significant figures. So the result should have 3 significant figures. And if you calculate it, you have the mass, which is equal to 166 grams per mole. So this is one information we can directly extract from the problem. Okay. Now, what else do we know? What if the expression for the carbon content, you know that it's going to be 12.01 times X divided by the molar mass. Same for the percentage of hydrogen. You know that is the molar mass of hydrogen, 1.008 times Y divided by the molar mass. We know that the percentage of oxygen will be equal to 16.00 times Z, very good, divided by the molar mass. So we can deduce X, and you don't forget, times 100, of course. And we have these values already here, here, and here. So we know that this is equal to 57.85. We know that this is equal to 3.64, and this one, 38.51. So we can deduce X equal the mass, molar mass of terephthalic acids, which is 166, times 57.85 divided by 12.01 times 100. And if you calculate it, X is equal to 8. You'll have 7.99, this is 8, okay? And you can deduce Y similarly. So we have 166 times 3.64 divided by 1.008 times 100. And you will get 6. Okay? And if you check the Z value, they have 166 times 38.51 divided by 16.00 times 100. And this is equal to 4. So we have X, we have Y, we have Z. So terephthalic acid formula will be C8H6O4. Okay, this is terephthalic acid. And I will give you a bonus by giving you the formula actually. So you have, let's see if I have place here. You have a benzene ring. Okay, and you have 2 carboxylic acid that are opposite to each other like this. And we can check, we have 1, 2, 3, 4, 5, 6, 7, 8, C8. We have 1, 2, 3, 4, 5, 6 hydrogen, and 1, 2, 3, 4 oxygen. So this is the formula for terephthalic acid. So here the idea is to again use the relationship between the mass, the molar mass, and the number of mole, and also how to calculate the percentage of any element from a molecule. Okay, and then you can solve this problem easily. Let's move to exercise number 4. A potential fuel full of rocket is a combination of pentaborane monohydride and oxygen. So here we have pentaborane, we have oxygen. The two react according to the following balance equation. So we have 2 pentaborane that react with 12 oxygen gas to give 5 boron oxide and 9 water in the gas form. And we can check that this is already balanced. We have 2 times 5, 10, 5 to 10. We have 9 times 2, so 18 hydrogen. So we have 9 times 2, 18. Oxygen, we have 24. So we have 5 times 3, 15 plus 9. So it's really well balanced. If one tank in a rocket holds 126 grams of pentaborane and another tank holds 192 grams of oxygen, what mass of water can be produced when the contents of the 2 tanks are mixed with each other? So here we have the mass of each of our reactants. So what is the first reflex you should have? Yes, calculate the number of mole for each of the reactants and check which one is the limiting reactant. But first, let's get the molar masses of all of the elements that we need. So we have borane with molar mass 10.81 gram per mole. We have hydrogen, this you should know it by now, 1.008, very good. We have oxygen. This one also you should know it by now. 1600 gram per mole. Excellent. So we have pentaborane. So B5H9. So the molar mass will be 5 times 10.81 plus 9 times 1.008. And it should be equal to 63.12 gram per mole. And the other one that we will need is borane oxide. So 2 times 10.81 plus 3 times 16.00. And this is equal to 69.62 gram per mole. What else do we need? We have oxygen. So O2, 16.00 times 2, 32.00 gram per mole. We also need for water, H2O. So 2 times 1.008 plus 16.00, 18.02 gram per mole. Okay, so we have all our molar masses. So let's start by calculating the number of mole for each of our reactant. So number of mole of B5H9. So it will be equal to the mass of pentaborane, which is 126, divided by the molar mass, which is 63.12. 3 significant figures, 4 significant figures. So result should have 3 significant figures. So here you should have 1 point normally 996 mole. You have 1, 2, 3 gram, 1, 2, 3, 4. So we should stop at 1, 2, 3, and this is equal to 2.00. And the number of mole for oxygen will be equal to 192 divided by 32.00, and this is equal to 6.00 mole. Okay, and from our stoichiometric reaction, we know that 2 mole of B5H9 gives 12 mole of O2. So let's say if I have 2 mole here, 2.00 of B5H9, I should have 2 times 12 divided by 2 should be 6. Here is 12, sorry. So 2 times 12, 24 divided by 2. So here 12. Okay, I should have 12 mole of oxygen, and this 12 mole is bigger than what I have, which is 6 mole. So I know that I don't have enough oxygen to react with all of my amount of pentaborane. So what is the limiting reactant? O2. So O2 is the limiting reactant. I don't have enough of oxygen to react with all of the borane, the 2 mole that I put at the beginning of the reaction. So the number of mole of water here and the mass of water that is produced will be determined by the quantity of oxygen that I put. So all of my calculation for the number of mole of water, I will use the limiting reactant, which is oxygen. Okay, so let's see that for 12 mole of oxygen, I should have 9 mole of H2O. Okay, so for the oxygen now I have 6. So if I have 6 mole of O2, I will have 6 times 9 divided by 12 mole of water, and this is equal to 4.5 mole of H2O. So now that I know the number of mole of H2O, I can deduce the mass, which is equal to N times the molar mass. Number of mole we calculated is 4.5, and you multiply it by the molar mass of water, which is 18.02. So the mass of water that is produced is equal to 81.1 gram. So for solving this type of reaction, just first check that the reaction is balanced, then get the molar masses of the compound that you need, then calculate the number of mole for the two reactants and determine which one is the limiting reactant. And the quantity of the limiting reactant will determine the quantity of the products that you will produce. And then you can calculate it like this one. Okay, so that is it for exercise number 4. Let's move now to exercise. The exercise number 5, so consider the following unbalanced reaction. So here you know that the reaction is unbalanced because it's already said here. Let me get my pen. So you know that it's unbalanced reaction. We have phosphorus to react with fluorine gas to give phosphorus tetrafluoride gas. Okay, so let's start by balancing the reaction. We have 4 phosphorus in this side, so we need 4 here. 4 times 3, 12. We have only 2. We multiply by 6. So our reaction is balanced. The next step to do is to continue reading the problem. What mass of fluorine is needed to produce 120 gram of phosphorus tetrafluoride? So we need to know, this is the unknown, we know it. We have produced 120 gram of phosphorus trifluoride, and the reaction has a yield of 78.1%. So what is the definition of the yield? We know that the yield is equal to the actual yield, the mass that you have from the experiment, divided by the theoretical yield that you should have from the balance equation, times 100. Okay. So in this problem, what is our actual yield of phosphorus trifluoride? We have 120 gram. Okay. And we don't know the M theoretic yet. This is our unknown. And we have times 100. And this is equal to 78.1. So to be able to solve the problem, we need the theoretical mass of phosphorus trifluoride. So let's get the molar masses first. So we have phosphorus P, molar mass 30.97. Fluorine F, molar mass 19.00 gram per mole. So we can calculate fluorine gas molar mass, which is 38.00 gram per mole. And of phosphorus trifluoride, it will be equal to 87.97 gram per mole. So we have our molar masses. Check. Okay, so we make good use of all of the numbers and all of the data that we have from this problem. So now, how are we going to calculate the theoretical mass that we need for phosphorus trifluoride? We are going to use first this equation. So we have this 120, 100, 71, 78.1. We need M theory. So let's calculate it. It will be equal to 120 times 100 divided by 78.1. So the theoretical mass is equal to 153.6 gram. We actually, from the equation, we need to use 153.6 gram of PF3. So this is the theoretical mass. From the theoretical mass, we can get the theoretical number of moles. Okay, and theoric for PF3 should be equal to the mass PF3 divided by the molar mass of PF3. Here it is equal to 153.6, and the molar mass is 87.97, and this is equal to 1.646 mole. Okay, and from our balance reaction, we know that to have 6 mole of F2, to produce, we'll need 6 mole of F2 to produce 4 mole of PF3. So if we have 1.746 mole of PF3, we should be using 6 times 1.746 divided by 4. And so we have N F2 that will be needed. It will be equal to 2.619 mole. And from the number of mole, we can deduce the mass of fluorine, 2.619 multiplied by the molar mass, 38.00, and this is equal to 99.5 grams. So this is the logic. You give the expression of the yield. From the expression of the yield, you know the theoretical yield that you should have, the mass, the theoretical mass for phosphorus trifluoride. And from the mass, you can get to the molar mass, to the number of mole. And from the number of mole, we can deduce the number of mole of fluorine gas. And from the number of mole of fluorine gas, you deduce the mass of fluorine gas that you should use. So you should use 99.5 grams of fluorine gas at the beginning of the reaction to produce 120 grams. You don't produce 153.6 because the reaction yield is only 78.1. So do you see the logic? Yes, so you have 99.5. If you use the stoichiometry, you should produce 153.6 grams. But the reaction has a yield which is lower than 100%. So not everything is transformed to PF3. Only some of it is transformed to PF3. And we know that that is actually 120 grams. Okay, if you have 99.5 grams of fluorine gas, you can produce only 120 grams of PF3. While if you check the stoichiometry, you should be able to get up to 153.6. So from the known yield, we go back to the amount of fluorine that we put inside our reactor. Okay, so you have to be able to go back and forth from the products to the reactants and from the reactants to the products. Okay, and always you need to check either the yield or what is the reactant that is the limiting reactant. So if you have the product, I will always tell you what is the yield. If it's 100%, like you fully convert everything, or it's less, give you the number so you can go back. Or if you have many reactants and I give you all of the masses, you need to calculate always the number of mole and check which is the limiting reactant to be able to know what are the products that are produced and in which quantities. Okay, so that is it for the exercise number 5. Let's move to exercise number 6. So consider the following reaction that is used to produce hydrogen cyanide, HCl, okay, which is toxic, by the way. How we need ammonia gas, 2 mole of ammonia gas, react with 3 moles of oxygen gas and 2 mole of methane gas to give hydrogen cyanide, 2 mole and 6 mole of water. Okay. So this is a reaction. We can check if it's balanced. So we have 2 nitrogen, 6 hydrogen, plus 8, so 14. And here we have 6 times 2, 12, plus 2, 14. We have 6 oxygen, we have 6 oxygen. We have 2 carbon, and 2 times 1, 2 carbon. So the reaction is balanced. If 5.00 10 to the power 3 kilogram each of ammonia, oxygen, and methane are reacted, what mass of hydrogen cyanide and water will be produced, assuming a yield of 85.0 yield. Okay, so here we have many information. We have the mass of ammonia, we have the mass of oxygen, we have the mass of methane that is used, and we have the yield. So what do we do first when we have this reaction? We checked it. This is to check if the reaction is balanced. Now we have the mass of all of the three reactants. We need to calculate the number of mole and know which reactant is the limiting reactant. And that will be the limiting reactant that will determine the masses for hydrogen cyanide and water. So first, let's go to check the molar masses of each of our compound to calculate the number of mole. So if we have ammonia, it's 14.01 plus 3 times 1.008, and the molar mass will be equal to 17.03 gram per mole. We need the molar mass of oxygen, 2 times 16.00 is equal to 32.00. We need the molar mass of methane, so 12.01 plus 4 times 1.008, and this is equal to 16.04. Okay, we need the molar mass of hydrogen cyanide, so 1.008 plus 12.01 plus 14.01, and this is equal to 27.03 gram per mole. We also need the molar mass of water. This one you know it by heart by now. So 2 times 1.008 plus 16.00 is equal to 18.02 gram per mole. So we have all of our molar masses. This is good. Check. Since we have the masses of our reactants, we can calculate the number of moles. So N for ammonia. Mass of ammonia, here we have 5.00. It's in kilograms, so we get it in grams. So 10 to the power 6 gram, okay? Divided by the molar mass, 70.03. And this is equal to 2.94 10 to the power 5 mole. Similarly, we get the number of mole for oxygen. Same mass, 5.00 times 10 to the power 6 divided by 32.00. And this is equal to 1.56 10 to the power 5 mole. And the number of mole for methane, same mass, 5.00 10 to the power 6 divided by the molar mass of methane, 16.04. And this is equal to 3.12 10 to the power 5 mole. So we have the number of mole of each of our reactants. Now let's determine which one is the limiting reactant. How do we do that? By using the balance reaction. So we know that 2 mole of ammonia should produce 3 mole, should be combined, because this is reactant, with 3 mole of oxygen. So how many moles of ammonia do I have? 2.94 10 to the power 5. If I have this, it should give 3 times 2.94 10 to the power 5 divided by 2 mole of oxygen, which is equal to 4.41 10 to the power 5 mole. And this is bigger than the amount that I have, bigger than 1 point, number of mole here of oxygen, 56 10 to the power 5. So I don't have enough of oxygen. Let's check the other reactor before we conclude. So we know similarly that 2 mole of ammonia should combine with 2 mole of methane. So if I have 2.94 10 to the power 5 mole of ammonia, I should have 2.94 plus 2 times 2 divided by 2, 2.94 10 to the power 5 mole of methane. And we compare it to 3.12 10 to the power 5. This is smaller, or we have more than what we need for methane. So we can conclude that what is our limiting reactant? The one that we don't have enough of. So we have excess of ammonia. We have excess of methane. This is excess. So our limiting reactant is oxygen. We can write that O2 is the limiting reactant. And we know that initially the number of mole is what we calculated before, 1.56 10 to the power 5. So this will determine my mass of hydrogen cyanide and also the mass of water. So this is what is asked, what mass of hydrogen cyanide and water is produced, but don't forget we have a yield of 85.0. So now let's calculate. Give the expression for the yield. The yield equal actual yield divided by theoretical yield times 100. So how are you going to get the theoretical yield? Yes, we're going to use oxygen, that is our limiting reactor, and the balance reaction to determine the theoretical yield for hydrogen cyanide and water. And knowing that the yield of the reaction is 85.0, we can determine the actual yield, okay, the actual mass that is produced. So let's do that. We know that 3 moles of oxygen should give 2 moles of hydrogen cyanide. So if I have 1.56 10 to the power 5, it will give 1.56 10 to the power 5 times 2 divided by 3 mole of hydrogen cyanide. And if you calculate it, it is 4. So 1.56 10 to the power 5 times 2 divided by 3. We can directly get to the mass. It's easier, or we can give the value, the intermediate value. Here is 1.04 10 to the power 5 mole. So of hydrogen cyanide. So we can deduce the mass hydrogen cyanide, that is theoric, okay, will be equal to 1.04 times 10 to the power 5, this is the number of mole, times the molar mass of hydrogen cyanide that we calculated previously, which is equal to 27.03. So this is the theoretical mass. And if you calculate it, this is equal to 2.81 10 to the power 6 gram, or 2.81 10 to the power 3 kilograms. Since our data was given in kilogram, you can calculate it also in kilogram. So this is the theoretical yield. So to get here the actual yield, we can use this equation. So we know that M of HCN actual will be equal to the theoretical yield, meaning 2.81, 10 to the power 3 kilogram, okay, multiply by 85 and divided by 100. And the actual yield will be equal to 2.39, 10 to the power 3 kilogram. Okay, so this is the theoretical mass of HCN, and this is the actual yield of hydrogen cyanide. Now, what is left to calculate is the percentage or the water amount that we produce. So we will use similarly here. We know that 3 mole of oxygen should give 6 mole of water. So if I have 1.56 10 to the power 5, I should have half of it, like this one times 6 divided by 3, so double. I should double this one. So if I have 3 mole of oxygen, it should give 6 mole of water. So if I have 1.656 times 10 to the power 5, I multiply by 6 and I divide by 3, so I double it. So it will be double. And I need to take into account the fact that you have the theoretical yield. So you can use the similar process to know that the mass of water actual will be equal to 0.85, which is the yield. So 85 divided by 100, multiply by 1.56, 10 to the power 5, 2 times, okay, like from the stoichiometry, and you multiply it by the molar mass of water, which is 18.02. And this is equal to 4.78 10 to the power 3 kilogram. Okay, so we can calculate our mass of water like that. So as you can see, then you can solve this reaction, this problem easily by first always check if the reaction is balanced. Okay, and here we have the masses for all of our reactants. So you need to calculate the number of mole as we did previously. Check which reactant is the limiting reactant, and the limiting reactant will determine the yield of all of the products. Here we also have the yield that is not 100%, so you need to take it into account to calculate the actual mass that you get. Okay, so we can calculate the theoretical mass using the balance reaction, and then you have to correct it with the actual yield, which is here 85%, so 0.85. When you multiply it, then you get the mass of HCN. You can use the similar process. I want you to do it. That's why I didn't do it here. You do the same from the 3 mole of oxygen, you get 6 mole. So if I have 1.65 10 to the power 5, I have the double. Okay, multiply by 2 here. That's why you get 2. And you multiply by the molar mass of water to get the mass, and you correct it with the yield 0.85, which is 85 divided by 100, and that's give you this mass of oxygen of water, which is 4.78 10 to the power 3 kilogram. Okay, so that's what all you need for this problem. Let's go to the last problem. Problem number 7. So sulfur diazine is a burn treating cream prepared by the following reaction. So we have Ag2O, which is silver oxide, that react with sulfur diazine. It react with this solid to give sulfur diazine and water. So if 25 grams of silver oxide react with 50 grams of this compound, what mass of silver sulfur diazine will be produced, assuming that the yield is 100%. So whenever you see yield 100%, means you can directly use the balance reaction to do your calculation, and you don't need to correct with the yield. So first check that the reaction is balanced. So 2 silver, 2 silver, we have 20 carbon, we have 20 carbon. We have how many oxygen here? We have 4 and 1, which is 5. 2 times 2, 4, and 1, which is 5. We have 20 hydrogen. Here we have 2 times 9, 18, plus 2, 20. 2 sulfur, we have 2 sulfur. So the reaction is perfectly balanced, okay? Now what we need to do, we have 2 reactants. This one, we know the mass. This one, we know the mass. So we need to determine the limiting reactants. Excellent. So let's start by the molar masses. So silver oxide. For silver oxides, for silver you have 107.9 plus 16.00, and this is equal to 231.8 gram per mole. Okay, we need to do the same for the other reactant. So we have 10 times 12.01 plus 10 times 1.008 plus 4 times 14.01 plus 32, if I'm not, yeah, 32.07 plus 2 times 16.00. And this is equal to 250.3 gram per mole. Okay, we have the molar masses. So we can calculate the number of mole. N for silver oxide be equal to the mass of silver oxide, 25.0, divided by the molar mass, 231.8. 3 significant figures, 4 significant figures. So we should have 3 significant figures. This is equal to 0.108. Okay, can calculate the number of mole for C10, H10, and for SO2, which is equal to the mass divided by the molar mass, so 50.0 divided by 250.3, and this is equal to 0.200 mole. From our equation, we know that 1 mole of silver oxide should react with 2 mole of C10, H10, and 4 SO2. Okay, so if I have 0.108 mole, I should be reacting it with 2 times 0.108, which is equal to 0.216 mole. So I need to compare 0.216 to 0.200. So I know that 0.216 is bigger than 0.200. So I don't have enough of this reactant. But this is my limiting reactant. Or we can say it, that Ag2O is in excess. So which reactant will determine the mass of my product? This one. So this is my limiting reactant. Okay. And I already calculated the number of moles. So I will use it to calculate the yield of silver sulfur diazide. So let's do that. So I know that 2 mole of C10, H10, and 4 SO2 solid should produce 2 mole of sulfur diazide. Okay, Ag, C10, H9, and 4 SO2. So it's 1 to 1. Okay, so if I have 1 mole of this one, I should have also 1 mole of this one. Okay, and here I know I have 0.200. So I have the number of mole of my sulfur diazide is equal what we calculated before, meaning 0.200. So I can calculate the mass of silver, sulfur diazide is equal to the number of mole, 0.200, times the molar mass that we calculated previously. We didn't calculate the molar mass of sulfur diazide. So let's calculate it here. So times the molar mass. And M here equal to the molar mass of silver, which is equal to 107.9 plus 10 times 12.01 plus 9 times 1.008 plus 4 times 14.01 plus 32.07 plus 32.002 times 16 for oxygen. And this molar mass is equal to 357.2 gram per mole. So the mass of silver diazide, I managed to do it, silver diazide will be equal to 0.200 times 357.2, and the yield is 100%. So here I directly get the mass, which is 71.4 gram. Okay. So whenever you have a problem like this, when you have the masses that are given for the reactants, you first calculate, get the molar masses here. So here we forget the silver sulfur diazide. So you need to calculate the molar mass for that one. Calculate the number of mole, get the limiting reactant here, which is, for here, this one is in excess. So our limiting reactant is this one. We use it to calculate the number of moles. So it's a 1-to-1 mole ratio. So we can, you know, that we have 0.200 mole. We calculated the molar masses of sulfur diazide. So we can deduce the mass of sulfur diazide that is produced. Okay. So that's it for this this recitation. So we go through 7 exercises. Always remember the relationship between the number of mole, the mass, and the molar mass, and also the relationship between the number of molecule and the Avogadro number. Okay, always check if you have many reactants, what is the limiting reactant to determine the mass of the products. Okay, and first of all, always check that the reaction that I give you is balanced. That's a reflex that you should have. Okay, so that's it for this recitation. See you again next time.